big key step there. I hit the record button. Okay, so other students will be able to watch this later. I will get this. I'm figuring out how to get this posted to YouTube, and then I can put a link on Blackboard. So this will be in there, and so I'll get some other videos uploaded as well. Okay, we'll do this sine of 2x plus 3 pi over 2. But first, I want to talk about the other function. There were 3 functions in the homework that we were going to graph. We were going to graph f of x equals a tangent of x, and that's in the book. And then we were going to graph f of x equals cotangent of x. I think that's in the book also, but I want to cover it because it's a little more involved, right? And then we'll talk about sine of 2x plus 3 pi over 2. Okay, so to graph, let me make this screen bigger here. Spotlight video. There we go. Okay. I think you can see that now. So we're going to graph f of x is cotangent of x. That's our goal here, all right? So the first thing we do when we say we're going to graph this function, what that means is we're going to graph the y value, or the outcome of this function, which is y. That's going to be 1 point. And what's the kind of the input for the function? Well, that's x, and here it's just x. It's simple. It's only x. Okay. So just to remind you, whatever's inside the parentheses of a trig function is known as the argument of the function. Okay. So in this case, our argument is simple. It's just x, and x is just a real number, and it represents theta. It's a measure of theta. But we could have more complicated functions in here, and we'll do that with that sine of 2x plus 3 pi over 2 in a little bit. We'll look at it. But so this part of it, we get a break on. This part is straightforward. So the graph we're going to make is going to be values of x, which is also happens to be theta, right? Because whatever's inside this argument, the whole thing, whether it's a function or something simple, but everything inside that argument makes up theta. So whenever you see the parentheses in a trig function, you know it's talking about an angle here, okay? And here our angle is just x. So our graph, let me find what I do with my pen. I had it laying here. So the graph is going to be of the points x and f of x, okay? That's the graph we're going to make. And f of x is just the same thing as y, right? Y is a name for f of x. So y is a dependent variable, x is an independent variable. And this represents a point, and we go get different values for x, and then we plug that into our equation here, and we see what the values for y are. And that gives us a grid, an XY grid. We just plot those points on the grid, and then we kind of connect the dots, okay? Well, sometimes the dots are easy to connect. Like after we've looked at sine and cosine functions for a while, we know what the shape of those is supposed to be. So we can kind of approximate, we can draw a few points on the graph to get the general shape of it. Maybe, you know, some high points and low points and a few points in between. And since we already know what the shape of a sine function or cosine function is, we can do a pretty good quick approximation of what those values would be between those points, okay? But with cotangent, it's more complicated, right? And even with tangent. And why is it a little more complicated? Well, here's the issue. okay? First of all, let's just think about cotangent itself. What is it? Well, we know that it's the reciprocal of the tangent of x, okay? The cotangent of an angle is equal to 1 over the tangent of the angle, okay? So we know that. But what makes it kind of complicated, if you will, is tangent itself is made up of two other trig functions, right? So tangent of x is equal to sine of x over cosine of x. So tangent of x is actually, it's a ratio, right? It's a value for the sine of x divided by the value for the cosine of x. And so to get the cotangent, we just take the reciprocal of that, so we flip that over. So once we flip it, this is what we end up with, right? So I could write up here tangent of x is by definition sine of x over cosine of x, right? And the reciprocal of that is we just do its inverse. We just flip it, because that's what the definition of cotangent is. It's 1 divided by that. So that flips it over, and we have cotangent of x is equal to cosine of x over sine of x. So we know what we're dealing with here, okay? And we want to graph this thing. So what we see here is we have a ratio, or you can think of it as a fraction, right? There's two values we have to determine, and in order to get a single point for cotangent, we have to determine these two values, okay? And then there's one further difficulty with it. It's not super hard, but it's a little tedious. It requires more work to figure out. And the issue there is we know that in math in general, you're never allowed to have 0 as the denominator, because that creates what's known as an undefined function, right? And basically, we don't allow undefined functions because we want to know specific values of everything. So we don't like undefined, okay? So this presents us with a challenge here. We're going to graph this thing, but we have certain values of sine of x that are not allowed. And when I say certain values, it's one number, okay, 0. 0 is not allowed for sine of x. But 0 occurs in many places in the sine of x, because recall the sine of x it is an infinite function, right? It just keeps cycling forever and ever in both directions, right? So everywhere where that function sine of x is equal to 0, at every point it's equal to 0, that's not allowed in our cosine of x graph, okay? So how are we going to deal with that? Okay, well, we'll back up for 1 second and recall right now we're just graphing the fundamental cycle, okay? And the fundamental cycle of a function, we know travels from the argument, covers the range from 0 to 2 pi radians. That's a fundamental cycle. So that's the angle, the entire angle, which is the argument, whether that's simple or whether that's some long function. The value of that whole thing is the angle, and that angle is going to cover the range from 0 to 2 pi radians, okay? And so that's all we need to graph for cotangent. And then we know that since it's a cyclic function, we know that that pattern just repeats indefinitely on both sides of that. Okay, so let's getting back to figuring out how we're going to deal with this. The sine of x is not allowed to equal 0. And just not to beat it to death, but that makes cotangent of x undefined, and that happens whenever x is a value such that the sine of x becomes 0. So there's certain values of x that aren't allowed because certain values of x make this sine function 0. Okay, so when we're hand graphing, we're not allowed to use values of x that are going to make this sine of x equal to 0. So what do? We get values of x that are very close to that, but not actually that point. We get values on either side of that point to see what the behavior of the function is near that point. The point itself becomes what is known as a vertical asymptote, right? So the graph can never take on a value there. As it approaches that point, the graph, as it approaches a vertical asymptote, the value in y changes dramatically the closer you get to it, but you never get to that point. There is no number you can assign to the value of the function at the point where the vertical asymptote is. Okay. Well, we're going to talk about that later. This one, let me get back to. So what we need to identify, let this get into focus here. I think that helps it focus if you do that. Let's see, yes. Okay. We need to identify the values of x that are not allowed then, right? So when is the sine of x equal to 0? And this is just a step by step, right? Well, the sine of x we know pretty well. When x equals 0, the sine of x is 0. And when x equals pi, the sine of x equals 0. When x equals 2 pi, the sine of x equals 0. So these are the values of x that are not allowed, okay? And just, so here's the sine of x, right? And this is x and y. So this is the point 0, 0, where it begins, the origin, right? And we see this function y is 0 when x is 0. And we travel up, this is pi over 2, this is a sine function, y equals sine of x. When we get back down to pi radians, y is 0 again. So x is not allowed to equal pi because this function is 0. And then the same thing, this is pi and this is 2 pi. So these are the values where our vertical asymptotes are going to be on our graph for cotangent of x. And let me back up 1 second here. So when we say we're going to graph this function, what we're going to get is pairs of values, right? We get a value for the argument, which in this case is just x. And so that's nice. It's just the x coordinate, okay, is part of the point, and the y coordinate is the value of the function itself, okay? So we get these pairs, x and f of x, which is the same thing as y, which is the same thing as the cotangent of x. Those are the points that we're going to get, all right? And we know we're going to have vertical asymptotes now. When x is 0, when x is pi, and when x is 2 pi, we're going to have vertical asymptotes. So what we have to do is figure out what's the value of the function when we're near those values, but not at them. That's what you're doing, okay, for those points. Let me see here. My phone was buzzing. I don't know if somebody was trying to text me. Just 1 second. Okay, sorry. I've told students to please call if they can't get through. That's why I had to check that, but we're okay. All right. So we've identified the values of x that cause sine of x to be equal to 0, right? And we had to do that again because in the cotangent of x, we have sine of x in the denominator. It's not allowed to be 0. So we want to determine behavior close to these points, okay? We want the value of y, or what is the same, we want the value of the cotangent of x when x is close to these points, but not at these points. Because otherwise our graph, we won't know what to do around those points when we're graphing it. If we're not at one of those points, we get explicit value for this function, right? We just plug in x and see what the cosine is. We plug in x and we see what the sine is, and we just do this division, and that gives us the number for this, which is y. So that gives us our data point. But when x are values such that this denominator is 0, we can't just plug everything in here, right? But what we can do is we can plug in values where x is close to the values that would make this 0, and see what the value of this function is as we approach that point, right? And so the way we think about that in our labeling is that we look at what's called x plus, okay? So if you think about it, so here's a point that's not allowed, x equals 0. This is a not allowed point. So what we want to find out is what is the value of our function when x is close to 0 but not at 0, and there's two ways that can happen. It can be slightly above that point, and we call that x plus. So we're approaching x from the right, okay? Or it can be a value slightly below that point, and we call that x minus. So we're approaching x from the left, okay? So then the next step is to look at this function and see what's going on when we're close to these x values that are not allowed, okay? So let's take the one where x equals 0. Let's look at the behavior around that point. So what we do for cotangent of x is we plug in cosine of x plus over sine of x plus. So that's that point that's just slightly to the right of that, okay? And when we look at this, we can do some approximations here, actually fairly easily, right? So if you know what the cosine function looks like, the cosine of x looks like it looks like a sine wave, only it starts at 1, right? Instead of starting at 0. So this is the value. So when x is equal to 0, at x equals 0, the cosine of x is 1, all right? If x is very, very slightly greater than 0, you can see from this graph that the cosine is still going to be pretty close to 1. It actually I didn't draw it perfectly here. This would actually fall off, you know, really slow here. But the point is, if you're very close to this x equals 0, the cosine of x is still going to be very close to 1. So this top number at x plus is going to be 1. What's the bottom number going to be? Okay, at I'll draw it up here. Here's the sine of x. And you just think about it the same way, right? So here's x equals 0. If we're approaching that from the right, we're approaching from this direction, okay? what's this function doing? It's getting closer and closer to 0, right? We know when x is 0, the function itself is 0, right? Because this is the point 0, 0 at the origin. But we can see here that as we approach this from the right, the value gets smaller and smaller and smaller, okay? So remember, we want an idea of what the value is at x plus, not at x equals 0. So what we can say here is that this is a very small number, okay? The sign of x plus is a very small number. We can also say it's a positive number, right? Because it's bigger than 0. We know that definitely, right? We know it's a positive number, and we know it's a very small number. The closer you get to 0, the smaller this is. So then what do we have? What we have is down here. So cotangent of x plus is 1 divided by, now this bottom number is arbitrary, and what I mean by that is just to get an idea to think about these things, you just think of a number that's pretty small, okay? There's no magic about which number you use. You just want a really small number. So I just put 5 decimal places out here and then a 1. But this could have been 15 decimal places, right? Or 30. The idea is you have some small number here so we can see what the behavior of the whole function is, okay? So for a small, and notice it is positive, it's a positive number. So both of these numbers are positive. So what we see here is at x plus, as we're approaching x from the right, our cosine stays pretty close to 1. It may be 0.99999, but it's something very close to 1. This number is getting very close to 0, but it's still a positive number, and it gets smaller and smaller the closer to 0 you get, right? So what happens to the ratio to this whole fraction here when you do this division in that case? You end up with a pretty big number. And also notice it's a positive number. Okay, so that's the whole point of this. At this undefined point, x equals 0, as we approach it from the right, we have a very large number, okay? And I haven't done it yet this morning, but you do the same thing. Now look at x, the behavior of x minus, okay? So we have cotangent of x minus. So now we're approaching x from the left, okay? We're approaching x from the left. So on our sine function, which is in the, and remember, this is cosine of x minus over sine of x minus, okay? So our cosine function, as we approach x equals 0 from the left, so here's the cosine function continuing, right? But as we approach x equals 0 from the left here, you can see we're already very close to 1, and we're getting closer and closer to 1. So this is approximately 1, right? And then in the bottom, what happens to the sine function here? Well, you can't see that. Okay, what happens to the sine function as you approach x equals 0 from the left? So back up here to the sine, let's draw the continuation of it. As we approach x equals 0 from the left, what's going on with the sine function is its value is getting smaller and smaller and smaller. It's approaching 0, okay? But a key point also is that it is a negative number. the y value is less than 0 as long as we're approaching x from the left, okay? So we have a very small negative number now when we approach from the left. So let's pick a very small negative number here. I'll say minus, and I don't have enough space here. I'm running out of room, but you'd have a bunch of zeros here, okay? A bunch of zero, negative 0.0000, small number, 1. Okay, so what does that make this cotangent x then? It's approximately, and so what do we have here? As we approach x from the left, we have 1 in the numerator and a very small negative number in the denominator. Okay, when you do this division, once again, you get a big number. Okay, but you got to recall you had a negative sign on this small number because of that, because of this sign function, right? This sign value is negative as you're approaching x from the left. And so this gets a negative number on it. And so the point here is also, if you think about this, as you get closer and closer to x, this top number is going to get closer and closer to 1. It's already almost 1, but it's just going to get closer and closer to 1 for a value. But this bottom number is going to get smaller and smaller and smaller. So what happens to this number? It gets larger and larger and larger. So it becomes that vertical asymptote, okay? So here's the idea. Let me pull something up and then I'll show you on the cat. Well, I think maybe you can see this. Yeah, you can see that. And I'll show you how to, this is a TI-84 if that's what you've got, right? But here's our origin, x equals 0, 0. So this the y-axis, that's the point where x equals 0. And that's a not allowed function, right? Because it makes the cotangent undefined. And you see here why it's undefined. Because if you get closer and closer to this point, to this 0 point, it depends on which direction you're approaching it from. If you're approaching it from the right, the number, the value of it's getting higher and higher and higher. Yeah, this is backwards when I look at it, but I think you're seeing it in the correct orientation. Anyway, as you approach x from the right, this line here is the cotangent of x. The function is getting higher and more and more and more positive, right? It never touches x equals 0. It just keeps getting bigger the closer and closer you get to it, but it never gets there. It never gets all the way to x equals 0 because it's unallowed, it's undefined. But if you look, if you approach x from the left, what happens to the function? This is cotangent of x. As you approach it from the left, the value gets, it's a larger and larger and larger number, but it's a negative number. So you're getting a bigger negative number as you approach x from the left. So, and this line actually never gets to x equals 0, right? But it keeps getting more and more extreme. It gets a larger and larger negative value. And so you can see here on this graph, this y-axis is known as a vertical asymptote. And you can also see it's not drawn in because it's not another axis, but if you look here at this point where my pen is, this is another vertical asymptote, right? And what is this? Going back to what we talked about earlier, that's where the sign of x is not allowed to be 0. That occurs at x equals 0, and that also occurs at x equals pi. So at pi, this would be pi, this point would be pi, because here's a vertical asymptote. You got the same thing going on about this line, it's just not drawn in. You could draw a dotted line in here, just like where this is a solid line. So this is a vertical asymptote. X is not allowed to be 0 because the function is undefined, and it's undefined because the closer you get this way, it's this huge positive number, but the closer you get to it from the other direction, it's a huge negative number. So it's an undefined number, the value of the function at that point. So this is another vertical asymptote. And there's one more, which the graph here is not big enough, but you see the start of it, and that's here. So this is at 2 pi, right? So we got an asymptote at pi. We got an asymptote at, an asymptote at 0, x equals 0. We have an asymptote at x equals pi radians. And we have an asymptote at x equals 2 pi. Because this would start, this pattern would repeat again on the other side, just like it did here. You would have a vertical line coming down here, and the pattern would repeat. And it does that in both directions. So the fundamental cycle is the area from 0 to 2 pi. So when you say graph the fundamental cycle, you would draw these two lines, okay? And you just approximate these curves in here. You get a couple points. You could get a couple points on either side of this 0 point here to see and plug them in, and you'll get an actual values. Oh, I don't know why that died there. There, screensaver, I guess. But you could plug a couple points in, a couple different x points in, you know, above this where it crosses 0, and then on the other side in order to get a couple of what these curvy points are, and then just kind of connect the lines. You know this is an asymptote, so you just approach it and you come down and then you start curving, and you can identify this 0 point here, right? Because this is where the function is equal to 0. And where does that occur? If you look at this, I know this is busy, but here's the function. Here's cotangent of x. So where is it equal to 0, right? Which is this, you know, the x-axis. When does this function cross the x-axis? So the y value is 0. Where is it that the y values are 0? Well, it's when this function's 0. And when's that going to be? It's when this is 0, right? Because the way sine and cosine work is they're not 0 at the same place because they're different in phase. So they're never 0 in the same place. So if you want to know when this function is 0, you just look at where the cosine function would be 0. And the cosine function is 0 at pi over 2 radians, okay? I think I drew that. Draw it again here. Well, yeah, here. So here's a cosine function. So this 0 point for it is at pi over 2 radians, right? And then it's 0 again at, well, I'm sorry. Let me think here. No, that's not pi over 2. I misspoke. That's pi. The cosine, or no, wait. I got to think here. No, it is pi over 2. Good grief. Okay, pi over 2 is this 0 point, all right? And so this next 0 point is 3 pi over 2. So the whole cycle is out here at 2 pi. So that's right. Sorry about that. Yeah, the 0 point is at pi over 2 radians for the cosine of x. And then there's another 0 point for cosine of x at 3 pi over 2 radians. And one full cycle, you know, starts at y equals 1 and ends at y equals. So this is a full cycle because we've traveled 2 pi here, right? the argument of the functions covered 2 pi. So that's the fundamental cycle of the cosine function. This would be the fundamental cycle of the sine function, because this would be 2 pi here. Okay. I want to show you on here, I don't know if you guys got the TI-84 or not, but this is relatively easy to graph on here. If you want to check yourself when you're drawing these out, if you just go into this stat plot, and it says y equals, this little button here says y equals, and you hit that, and you type in what your function here is. Now, I don't know, I haven't tried it yet. I don't know that cotangent would work if you just type COT. I'm not sure if this calculator knows what that is or not, but it definitely knows what the sine and cosine functions are, right? Because it's got buttons on them for sine, cosine, tangent. So I wrote the cotangent function, I just typed it in here, y1 equals cosine of x divided by sine of x. That's all you got to do. You just put that in there, and then you hit, you can hit this graph button, and it graphs it. That's one way to do it. Okay, and there it's graphed. Now it doesn't give you the numbers, but this is the correct graph for that, and this can help you when you're doing your graphing, right? You can go put things in tables and get it to display some numbers as well. I'm not going to get into that right this minute. One thing I do want to show you back to this, I did this morning, and I got an error, and it came up and said error, something about dimension mismatch or incorrect dimension, and I kept getting that error. Okay, and so what the problem ended up being, if you go into this other menu, let me find it here, stat. Okay, if you go into this stat menu and then edit, and see where it gives you L1 and L2 lists. Because this is used sometimes in graphing also. This is where you can put point values in. But these lists were different lengths, okay? I had more points on one side than on the other side. And even though it's not really using these, it's not using these lists to draw that graph that it just drew. But the software, it's tied into it, and it knows that these lists weren't the same, so it gave you an error, but it's not even really using these points because I put actual values in here, and it's not plotting these points. So it's not actually even using this to make that graph, but because these lists had a different length, that gave it an error, because sometimes it does use these lists when you're doing those graphs, okay? So these lists, L1, L2, have to be the same length. And it doesn't matter how long they are, or what the numbers are when you just want the raw graph the way we got it. So y equals, type your function in. You can hit graph, or I think on here you can hit zoom. Here's the zoom button. You can hit zoom. That gives you a bunch of functions. And here's a trig function down here, 7. So zoom 7. And it draws it for you. You can watch it draw it. So you can see the vertical asymptotes pretty good on here, okay? At x equals 0, x equals pi, and x equals 2 pi out here. Okay. So the process for making a graph of cotangent x, and I may continue this in a part 2, but you've seen the meat of it, if you will. But again, we're doing a fundamental cycle, so we take our angle, which is the whole argument, which here is just x, and we got to go from 0 through 2 pi, and we'll do it in increments of pi over 4. So pi over 4, 2 pi over 4, etc., till you get up to 7 pi over 4, 8 pi over 4, which is 2 pi, right? And then you can just Now, to get this number, okay, what you can do is there's not a button on your calculator for cotangent, but you could write a very, very small program and put it in there. Or there may be some function in here that I haven't researched yet where it's actually in here, but the buttons on the top of the keyboard don't show cotangent. But what you do is you just do the division. You just take x, you plug the value in, and you could make your table. You know, you could write cosine x, if that helps you, and sine x, and just record what those values are for each value of x, okay? And then when you've got these values in your list, you just do this division. You just divide the cosine by the sine, and that gives you the value, okay, for cotangent, which is what you're graphing. So when you say make a graph of this, we're graphing the pairs of points that are the argument, which here is very simply just x, and the value of the function, which f of x, which is y. The value of the function is the whole thing, okay? And here it's just cotangent of x, so that's the value, that's the y value. And to get that, it may make it easier if you make a little table and record the cosine and sine, then you can do the division. That gives you the value. And then for each point where we had trouble, where x was going to cause the sign to be 0, you need to plot a point, you know, very slightly above that x. You need to put an x value in that's just a tiny bit bigger than that x value. Okay, and so that occurs at x equals 0 is one of the places. So to get, you won't get a value here because it's undefined. So I would put 0.0000, you know, some very small number, and that'll give you, that'll show you, in this case, that you have a very large number close to x plus, okay? So you know your graph's coming up. Then you could just play around with it. You could put a very slightly bigger x in and see that this number comes down some in value. That just gives you the general idea of the shape of this line, okay? And even though we started at x equals 0, you could put negative in some very, very, very small number. That would show you that you have a very large negative number close to x equals 0. So that takes care of the graph around this point. But we're graphing the fundamental cycle, which just starts here and goes to 2 pi. So it doesn't really include this part. So for the 0 point, you can just do plus x, you know, a very, very small amount of 0 plus a very, very small number, and then maybe add a slightly bigger number, but still small. And just, you know, pick any number you want. Just add a small increment to that number, and you'll see the line comes down a little bit for that function. And then you have to do that again at x equals pi, right? You have to put pi plus some very small number, say 0.00001, and then you'll see you have a very large y value. And then you can put pi minus a very small number, so pi minus 0.001, and that'll give you, show you that you have a very large negative number close to that point. And you can just draw a couple points, you know, around these asymptotes, and then you just kind of approximate and draw it in yourself with your eyeball. But you do get, so you have to do the plus minus thing around this 0, and you have to do it around pi, which is here, right? 4 pi over 4, that's pi. So we've gone from 0 to pi to 2 pi. And you have another, so you have undefined points here, here, and here. The rest of these, you just make your table, and they'll give you these points, right? You'll have a hard number, and just write it out to like, you know, you can just jot it down to like 3 decimal places. And then on your graph, just kind of, you know, rough it in. Okay, so that's how you would graph y equals f of x cotangent of x. Tucker says, on my homework, I just put undefined for even though I know it approaches but never. Is that okay? Or would you rather change that and resubmit? It's probably okay, Tucker. I'll look at it, but don't worry about it. I'll get back with you if you need to do something different. It's undefined. You just want to draw in, you know, you just want to just get an idea of how fast this line's changing, you know, a couple points. So you know the asymptotes there. So you want to see this shape in your graph, okay? And so you want to get yeah, I was trying to. You could pick. Well, it gives you. I mean, undefined is good. If you understand how to draw this, that's good enough. If you understand this is the shape and that's why it's the shape, you can just draw this shape and you're good. Okay, just make sure you have these points that where you do have hard, you know, explicit numbers. Make sure you have those points on the graph so you can see them. So that'll be good enough. All right. Alexis, let's get back to the other problem you wanted to see. Graphing the fundamental cycle assigned 2x plus 3 pi over 2. Excuse me. Let me see here what we got. Yeah, okay. Move that. You can see that all right. Okay, so we do a fundamental cycle of theta. So what's theta? Theta, remember, is the argument. What's in the argument? It's the whole thing. So this whole thing is the angle theta. So what we're graphing is a fundamental cycle of this function. So theta has to travel, same thing, theta has to travel from 0 to 8 pi over 4, which is from 0 to 2 pi. And we go in chunks of pi over 4 chunks to get there. Okay, so that's theta and sine of theta. Okay, but now when we say graph the fundamental cycle of this, what we're really saying is to graph the points x and f of x. Okay, that's what the graph is. So here, yeah, you can see that. So here, this whole thing is theta, and you need to make this table, okay, because this is going to help you a lot. But what you're graphing, you're not graphing theta and f of theta, you're graphing x and f of x, okay? So you have to determine if this is theta, then what is x? Okay, and that's straightforward. This is theta. This whole thing is theta, right? So you just solve this for x. And I believe I've done that here. Yeah, and then the other point I was going to make was, so we got to figure out what x is at these values of theta. What is the x value at these values? Because we're graphing x and f of x, okay? But f of x is easier. F of x is just the function itself, whatever the thing was. And this could be an even longer function, but it's the whole thing, okay? And so here it's just sine of theta, because we said this whole thing is theta. So the f of x is just the sine of theta. And if we just write down these thetas, there's nothing to figure out there. We'll just write them down. And we can just plug in theta to the sine function, and we get these values. Well, that is y, which is f of x, right? So we have all these values for our graph when we do this. but we just need to get x, because when we say graph this cycle, we're talking make a graph of x and f of x. And so you have to know what x is. And so you solve for x. And I did that here. I just wrote down all the steps so you could see them all. But so this was the angle, or here's where we start. And this is just an x here, okay? That's kind of messed up looking, but this is just 2x plus 3 pi over 2. That's what's in the argument. That's the whole angle. That's theta. So you want to get x separated by itself on one side of the equation. It's just regular algebra here, okay? So we subtract 3 pi over 2 from both sides of the equation, okay? So here we subtract 3 pi over 2 from this side, and we subtract it from theta. We start here, subtract 3 pi over 2 from both sides. That cancels here. So now we have theta minus 3 pi over 2 equals 2x. So we divide both sides of the equation by 2 in order to get rid of this 2. Okay, then these 2's cancel, and we end up with this. Theta minus 3 pi over 2, this whole thing over 2 equals x. Right? And then you could just flip that around and say x equals this. So it's not backwards looking. But then the next step, I just simplified it, right? This is theta over 2 minus 3 pi over 2 over 2, right? I just wrote that out. So theta over 2, and then you simplify this one. 3 pi over 2, the whole thing over 2 is equal to 3 pi over 4. So x is equal to theta over 2 minus 3 pi over 4. That's what x is, okay? So now we have our table. We have theta, which fundamental cycle, we got to go from 0 to 2 pi. We do it in chunks or increments of pi over 4. And then we can just, we can use our wheel, right, to get the sine values of theta. Because you just look up your angle on this wheel. Here's pi over 4, so this is theta's pi over 4. The sine is always this second number, right? This is the x and y coordinate, which on a unit circle, this point on the unit circle, okay, for a given angle, this is the cosine of that angle, and the second number is the sine of that angle. We demonstrated that earlier, okay? So you can just look at this wheel, and the sine of all these angles is this second number all the way around. So we got the value for pi over 4, excuse me. Then we get a value for 3 pi over 4. Here's the sine of that. Value for this would be 4 pi over 4, right? Pi equals 4 pi over 4, right? Sine of that's 0. And we can get the sine of 5 pi over 4 here, etc. This would be 3 pi over 2, which is the same as 6 pi over 4. And here's the sine. And you just travel around the circle. That gives you your sine values. Okay, so we've got theta and we've got sine of theta. So sine of theta is f of x. That's the same thing as f of x. So we've already got those points. We've got 1/2 of the point we need for our graph, right? We just need to know what x is. And then all we do is we take, here's the equation for x. Okay, so we take each value of theta, we take pi over 4, and we plug it in for theta. And that tells us what x is when theta is pi over 4. And I just wrote all that out here, okay? It looks more complicated than what it is, but I just wrote this out, that x is equal to this. And you just take the value for theta and plug it in here for each one of these values. And then you do the subtraction, the arithmetic. And so you get minus 5 pi over 8, and that's the x value, okay? So this is x here in this last column. This is how you calculate x, but it's just using this formula, okay? You could make a table and just put x in it and not have all this stuff, you know, if that's too busy to look at. But I just wrote it down so you'd see where this came from. It's just getting x from theta. Given theta, here's x. And then when you make the graph, you just plot the points. Here's your x value, and here's your f of x value, which is sine theta, right? So we plot x and f of x, and f of x is sine theta for this problem. Y equals f of x equals y equals f of x equals a sine of this thing is theta, all right? So that's y. Y is the sine of theta. So we got the y values here, which is f of x, and we just need the x value, and we just had to do this arithmetic up here. We know that the whole angle's theta, so then we just solve that for x. Well, what is x? If we know what theta is, what is x? And all we did was just solve this for x. Does that make sense? I got messages here. Okay, Tucker, thanks for tuning in. I hope you have a wonderful day. And I'm going to post this video. I did hit the record button. Thank goodness. I've done a few of these videos where it did not record. That's kind of irritating, but we got this one. So this will be posted on Blackboard. There'll be a link, and it'll be a YouTube video. So are you good, Alexis? Do you have any more questions right now?
How do you get the 6 pi over 8 when you're solving for x?
Okay, so let's do that. So are you talking about here, this first?
Yeah.
Okay, minus 6 pi over 8. Okay, so you start with theta. Theta is 0, okay? So all we're going to do is we're just going to plug 0 in for this theta value in this equation. So x equals 0 over 2 minus 3 pi over 4. So x is minus 3 pi over 4, all right? But once I started doing these, I noticed some of the values came out of so many pi over 8. So what I did was I just made all of them. I made 8 the denominator for all of them. Now, I did not change the value of them, right? Because I'll show you that. Get a blank piece of paper. Okay, so what we've got is negative 3 pi over 4. And I just noticed a pattern when I started doing this, that some of them came out with so many pi over 8. And just to make it easier on graphing, I wanted to make the increment the same on all of them, okay? So instead of having some things were written over 4, I wanted everything written over 8. So how do I convert this to get something over 8, right? Well, you notice if you multiply 4 times 2, that gives you 8, right? But we're not allowed to just do that because then we've changed the value of this thing. But if we multiply this whole thing by 1, all right, minus 3 pi over 4 times 1, and we use a special form of 1. 2 divided by 2 is 1, right?
Yeah.
So 2 times 4 is 8, and 2 times negative 3 pi is negative 6 pi. So that's what I'm doing there. Because some of them came out in the answer when I worked them out, they just already came out as something over 8, but some of the answers are something over 4. So I just made them, I converted them all into something over 8. So when you graph it, you got the same jump every time in value. You got, so you'll notice here, the x values start at -5. Well, they start at -6 pi over 8. The next one is -5 pi over 8, then -4 pi over 8. So they're just increasing by pi over 8 each time. So that makes it easy to graph. When you draw a graph, you can draw equally spaced divisions, and each division is pi over 8. One division is pi over 8, and we start at -6 pi over 8, and we go up in divisions by pi over 8 each time until we get all the way up here to +2 pi over 8. And let's see if we can, and this is a rough graph of that, okay, of that function. So here I'm showing you those divisions. So I didn't write them all in because it would just be too busy, but like this would be -7 pi over 8, excuse me, -5 pi over 8, -3 pi over 8, etc. So this is 0 pi over 8 because it's 0, right? So this is pi over 8, 2 pi over 8, 3 pi over 8, etc. 4, 5, 6. This made that easy, so it'd be easier to graph. Now let's go here, just while we're playing around, let's put that in the calculator here. So if we say y equals, and we can say delete, 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 right? And we'll put this function in. So we'll just say sine of 2, and x here is there, plus 3 pi over 2, okay, divided by 2 in parentheses. So can you see where I put that in here?
Yeah.
Sine of 2x plus 3 pi over 2. And I just hit this y equals button to put that in. All right. Then you just hit the graph button. Now that's doing the whole thing. And we want just the fundamental cycle, right? So the part of it we want is just the part from theta equals 0 to 2 pi. And when theta equals 0, the x at theta equals 0 was -6 pi over 8. So our function starts here. But, it would continue on, in both directions. It goes on forever, right? But we're graphing the fundamental cycle. So that's just from here to here. And that's, you can see that on their plot. So it would start, at this same point. It would start right here. And it goes through one cycle, which ends here. Okay? Any other questions?
No, that's it.
Okay. Well, thank you very much. Have a great weekend. I'll be posting some videos and some other things on Blackboard, you can look at. No big assignments over the weekend. You might want to just keep looking at 10.5, just to get an idea what these graphs look like. And if you got a calculator, play around with it and just look at some of them, okay? All righty. Are you gone? Hello, hello, maybe I lost you. Oh, okay. Thank you. Have a good one. Adios.